Okay, let me start from the uniformly elliptic case. Okay, so the model example I'm going to talk about is this kind of equation. So I get a nonlinear operator, which is potentially degenerate, and the right-hand side is in the most general case a measure. So in this case, solutions should be defined in a proper way. There are not exactly distributional solutions, but I would like to focus on a priori regularity estimates. Once these estimates are obtained, then approximation arguments can get you to more general solutions. So the assumptions I'm going to consider are very, very general after Lagichenska and Duhaltsev. And this is a classical topic. And a typical instance when P is different than 2 is given by the P Laplacian operator. But what I would like to say is that all the results I'm going to talk about are non-trivial already in the case when P is equal to 2, referring to the nonlinear case. And the emphasis is on Lipschitz estimates. So what I would like to talk about is a general program of linearization of these equations. And the ultimate goal is to show that you can treat these nonlinear equations as they were linear in essentially every respect from the regularity viewpoint. Okay. So how do you get Lipschitz estimates and gradient estimates when you're dealing with the classical Poisson equation? I mean, a classical way that was probably known already to Gauss was to use fundamental solutions. Therefore, any solution can be obtained via convolution with the fundamental solution, that's Green's function, and this translates into the fact that you can pointwise bound the gradient via Riesz potential operators. Once you know this, and this is pretty straightforward and classical, then as you know the action of this operator in essentially all reasonable function spaces like those of rearrangement invariant type, then you can get all the estimates you like. Of course, this approach is purely linear. And there's no way a priori that you can imagine that this translates into a nonlinear effect. But this is not the case. This is Marcel Louise, and it's a classical picture of the time. Okay, but now let me give you the first, this general linearization principle. Okay, imagine to do the following very brave heuristic. So you formally rewrite this equation into this linear equation where B is equal to this vector field, this nonlinear vector field. So if you concentrate on this equation, this is not an elliptic equation because you can add any curl, any a priori regular curl and get all the stuff you like. But you can always solve this equation. That's in fluid dynamics known Bogowski's lemma, as Bogowski's lemma. And how do you solve it? You essentially apply a Riesz potential to both sides. A Riesz potential is an integration, and therefore if you apply this to both sides, then you get that V can be estimated by the Riesz potential. Of course, you don't know that your V is of this type because you can get infinitely many solutions. But if it were the case, then the equation, what the equation is telling you is that you can pointwise bound what you get under the sign of divergence, whatever it is, which is equivalent by coercivity to this power of the gradient by the Riesz potential. So the equation is telling you that there could be a linear estimate. This is in fact what we have proved in a certain number of papers, especially with Tuomo Kuusi from Helsinki. So the rather crazy estimate we were able to prove is that whenever you have such an equation, such a nonlinear equation, then you can always pointwise bound what you have under the sign of divergence with the Riesz potential of the right-hand side measure plus a localization term that must be there, because when capital I goes to 0, you get A and A, while when capital I goes to plus infinity, this last term disappears. So essentially, this estimate tells you that the whole theory can be linearized. And this is essentially the meaning of the estimate that tells you that you can, from the point of view of the gradient estimates, you can treat this equation as it were linear. So if you want to have gradient estimates, you just don't look at the equation anymore. You just look at the mapping properties of the Riesz potentials that are well known in every reasonable setting. And therefore you end up with that. This has been proved, and the central paper is a paper on ARM with Tomoku's and myself. This has generated a very wide literature, by the way, because the idea is that you can really linearize the regularity theory after this estimate, because you don't have to do anything. And in particular, when you let capital R to plus infinity, provided you have reasonable decay properties, you get with this very synthetic estimate that tells you that any general nonlinear equation of this type can be treated from the point of view of the gradient estimate as it were the Poisson equation. So there is a ghost of the fundamental solution. You can always define, of course, the fundamental solution as a solution to this equation when mu is a Dirac delta charging the origin. But of course, what you cannot do because you're in the nonlinear setting, you can get any solution by convolution. This estimate tells you that you actually can, and there's a ghost of a fractional integral. That's the convolution. And these results have been more recently extended to the vectorial case too, when you need to consider the purely Laplacian system. Otherwise, the result is in general false, because already when the right-hand side is equal to 0, for any elliptic system, you get singular solutions. But for quasi-diagonal systems, first investigated by Nino Realzev and then by Karen Uhlenbeck, then you can get this estimate. And the proof is completely different in this case from the scalar case. It involves a very delicate combination between epsilon regularity arguments, which are typically originated in geometric measure theory after the work of De Giorgi and Almgren, and then translated by Uhlenbeck first, and then authors like Jaguint and Modica in the setting of systems. But the outcome is always the same. You can, in fact, linearize the theory. Okay, just let me show you how estimates of this type can get you in one shot, for the model case, the basic results that were known in the literature. So if you concentrate both in the equation and in the system case to this model example, you immediately get as a corollary the higher integrability results of Ibanez and Di Benedetto Manfredi. You can get in the nonlinear setting the results of Adams in Murray spaces that are very classical. You can get all the basic results of measured data problems theory from Boccardo and Gallou, and moreover, you can extend the theory to the vectorial case. This was still a missing point. So in one shot, you can extend these results to the vectorial case immediately, because essentially you are treating these equations as they were the Poisson equation. And then also the classical Talentis estimate via rearrangements can be obtained. And then also in the vectorial case, the main points of a very nice papers by Dolzmann, Unkenböller, and Müller can be obtained in the setting of local estimates by the previous estimate. So essentially, whatever you can do for the Poisson equation, you can translate verbatim to the general case of quasi-linear, potentially degenerate equations or the P-Laplacian system. So there's no difference whatsoever. Moreover, you can fix a certain number of borderline cases that remained open because of the nonlinear setting, but now the nonlinear setting has been bypassed and has been reduced to the linear one. This is in fact a general principle, because this theorem by Paolo Baroni tells that whenever you have a divergence for uniformly elliptic operator, uniformly elliptic means that this condition, first introduced by Gary Lieberman many years ago, is satisfied, then whatever you have under the sign of divergence, you can pointwise bound via the Riesz potential as it were linear. So once again, for all these kinds of equations, the previous results can be extended immediately. So without any effort. So you don't have to go to a priori estimates, you don't have to go to different techniques. But you can go a bit further, and you can even get a continuity criterion. Just let me show you how you can get other nonlinear analogs of classical linear results in a verbatim, essentially. So this is the Riesz potential of the right-hand side. If you assume that this quantity is in L infinity with respect to x, then this is, of course, the localized Riesz potential. It's smaller than the Riesz potential. It's the localized Riesz potential Well, if you assume that this quantity is in L infinity, then you know that the gradient is bounded. If this quantity is pointwise bounded, then by absolute continuity of the integral, then it goes to 0 pointwise with respect to x. Now, assume that you're reinforcing this, prescribing that the measure doesn't charge n minus 1 Hausdorff dimensional sets enough to get that this quantity goes to 0 uniformly. So you are saying, in a sense, that the measure is not charging sets with too small Hausdorff dimension. That's the real meaning. Okay, then you can conclude that the gradient is continuous. Corollaries. Then you can get an analog of a classical result of Stein. So this classical result of Stein identifies the largest space you have to prescribe the gradient to belong to in order to get that B is continuous. So essentially, this is an extension of the classical Sobolev-Maury theorem. You know that when the gradient belongs to a length plus something, then B is Hilbert continuous. If this plus something goes to 0, then you want to identify the larger space, okay, in the smaller space, and actually the larger space, dV has to belong to guarantee that V is continuous. This turns out to be the very classical Lorentz space, which is defined in the following setting, in the following way. So you prescribe that this measure, the measure of the level sets of the function G, decay fast enough in order to make finite this integral. So an example is given essentially by correcting power type equations by a log. So the log is essentially the second index that turns the first one. These are interpolation spaces. This means that if you have an equation of this type, so Laplacian that belongs to Ln1, then the second derivatives belong to Ln1, and then the gradient is continuous. Okay, now the point is that now you notice that if mu belongs to Ln1, the continuity criterion is satisfied. So the risk potential does go to 0 uniformly with respect to x, and therefore you get that the gradient is continuous. So in other words, you pass from the classical linear theorem of Stein that tells you that Laplacian belonging to Ln1 guarantees continuity of the gradient. Well, you pass from the linear classical theorem to the nonlinear Stein theorem that holds both for equations and the P-Laplacian system. So if you want to guarantee the larger space, this has to belong to guarantee that the U is continuous, then you get the same result when you go to the nonlinear uniformly elliptic setting. So that's what you get. And this goes in the spirit of the previous results that tell that this linearization principle does make no difference between the Poisson equation and any general equation, whatever the growth is. Okay, now let me identify a very recent connection with the so-called nonlinear Calderon-Zygmund theory. So risk potentials have something to do with fractional integrals. They are fractional integrals, in fact. And so with fractional integrals, you can control the size of the gradient. Now we go to maximal regularity in the sense of maximal differentiability of the gradient, because that's a parallel here. We have seen that there's a ghost of fractional integrals because there's a ghost of the fundamental solution. Now I'm going to show you that there's a ghost of singular integrals too. Let me recall something which is very, very fashionable these days. These are Sobolev-Slobodevsky spaces. Actually, this is one possible way to describe fractional Sobolev spaces. Then there are Calderon spaces, Biezov spaces, Nikolsky spaces. This is the one that goes via Sobolev-Slobodevsky spaces and via the so-called Gaillard-Honor. So you fix a parameter between 0 and 1 and an integrability exponent gamma. And you prescribe that the oscillations of V measured in the L gamma sense go to 0 fast enough in order to compensate the blow up of this kernel. And then you say that this belongs to WS gamma. This quantity, intuitively speaking, scales as an S differentiability, and these spaces, they come along with their fractional Sobolev embedding theorem, which is an interpolation fact indeed. Okay, now observe that this is the classical failure of the Calderon-Zygmund theory in the borderline space. When the right-hand side of the Poisson equation belongs to L1, or even worse, is a measure, then this is not guaranteed in general. So apparently, there is no analog that you can get for also in the nonlinear case. Nevertheless, for solutions to general nonlinear problems, you can still prove that what you have under the sign of divergence belongs to any fractional Sobolev space before the forbidden one. So this is essentially the best result you can get in terms of Calderon-Zygmund theory in the limiting case. And this holds for general equations, for general nonlinear equations. So once again, you get an analog of this result. And this gives exactly the same phenomenon that tells you the same result for the linear equation via fundamental solutions. So if you use fundamental solutions, you cannot get that the gradient is differentiable, but you can still get that the gradient is in W sigma 1 for every sigma less than 1. And then we prove, and this is a very difficult proof. It actually takes more than 50 pages, but the statement is very simple, that you can linearize this fact as there was a fundamental solution. So the idea is, once again, to pursue this general linearization program in every scale. Okay, once again, this comes along with a suitable Cacciopoli type energy inequality that that allows you to estimate locally the Gallardo norm of the vector field A in terms of A itself and the measure. So this is a classical Cacciopoli type inequality. And these are inequalities allowing you to bound higher order derivatives by lower order ones, plus that. And the data are scaling in the natural optimal way. So this extends an earlier result for p equals to 2 in a previous paper of mine, and actually solves a conjecture put in that paper. This is Cacciopoli. That's the second picture I'm going to show today, and the last one too. So let me compare the two linearized estimates. So let me summarize what you got up to now. You get a nonlinear equation. So you get the ghost of fractional integrals because you can pointwise bound the gradient via a of du, and this grows as du to the p minus 1, so it incorporates the scaling of the equation. And you can prove that there's a ghost of singular integrals by pointwise bounding the Sobolev norm. So in other words, there are ghosts of fundamental solutions, although you cannot use fundamental solutions via convolutions. Just let me observe the remarkable fact that both these statements are p independent. So you don't see p here. P just appears in the constants implied by these symbols. So it's this concludes this linearization principle. So this is as far as the uniformly elliptic setting is done. So let me point out other, interesting results. In the energy range, there's another interesting vectorial paper by these authors. Then there's a paper by Cianchi and Mazia, and that's an interesting paper where Cianchi and Mazia, they give a rearrangement global version of our estimates. So we prove that you can pointwise bound the gradient via the Riesz potential. They prove, when you assume global boundary data, that you can globally bound the rearrangement of the gradient via the rearrangement of the Riesz potential. So of course, in a global way, this estimate follows by the local one if you get it globally, because you take rearrangement controlled by the rearrangement. Otherwise, you get a global version. Then there are other linearized estimates by Dinin, Kaplitsky, and Schwarzacker, and there is a recent nonlinear Calderon-Zygmund theory paper by Balchi, and Weimer. Okay, now let me come to more recent results, and they are about non-uniformly elliptic equations. So as you see, from the point of view of the Lipschitz estimates up to now, essentially, we have this nonlinear Stein theorem. This nonlinear Stein theorem tells you that if the right-hand side belongs to Ln1, which is a space that is P independent, then the gradient is continuous, and this extends to the nonlinear setting. And these results are obtained in the setting of uniformly elliptic operators in the sense of the P-Laplacian type. Uniformly elliptic, as we are going to see now, I mean by uniform ellipticity the fact that the ratio between the highest and the lowest eigenvalue remains bounded away from 0 and plus infinity. So the idea is that what it really matters in this equation, as soon as you have a bit of ellipticity, is not really the specific form of the ellipticity you get, but the fact that the equation is in divergence type. And therefore, you treat it as it were a linear equation in this nonlinear vector field. So the duality principle of this linearization program tells you that these equations in our approach should not be considered as nonlinear equations in the gradient, but as linear equation in a nonlinear vector field of the gradient. And therefore, you just treat it as it were linear, but only formally. So this has been done in the uniformly elliptic case. And now I would like to go to the non-uniformly elliptic case. Okay, for this, I'm going to go to integral functionals of the calculus, so variations. And I'm going to restrict, for reasons that maybe are too long to explain now, but to these kinds of integrals. And of course, if you formally write the Euler-Lagrange equation, then the equation is of the type that we have seen before. Now, if we take this specific choice that gives you back the P-Laplacian operator, well, you see that the matrix of second derivatives of f then has lower eigenvalues bounded from below by the gradient to the p minus 2, and from above by the gradient to the p minus 2. So it's degenerate because when, take for instance the case p larger than 2. When z goes to 0, then this eigenvalue disappears. And when z goes to plus infinity, also the highest eigenvalue disappears. But the ratio, which is really the quantity that matters in these equations, the ratio is uniformly bounded. So the ratio is uniformly bounded. So in this sense, this equation is degenerate, but is uniformly elliptic. Okay, so now I'm going to talk about the same type of integral functionals, but in the case this ratio is going to plus infinity. This is the quantity that enters into all regularity estimates, especially those ones that you try to do when you want to prove that the gradient is bounded. And there's obviously a competition here, because what you want to exclude is that the gradient is bounded. So a priori, the gradient can go to plus infinity. But if it goes to plus infinity, then you lose the information. So there's a balance, and we are going to see a balance that the idea is that if this ratio is going too fast to plus infinity when z goes to plus infinity, then you lose regularity. Otherwise, you can get back to the usual case. The focus point in these kinds of problems is to prove that the gradient is bounded, because the whole problem here goes to plus infinity. You see the whole problem at plus infinity. Okay, this is a very classical topic stemming from operators of minimal surfaces type. There are very, very classical papers by Lagishenskaya and Uraltseva, by Leon Simon, by many, many people. And in the setting of the calculus of variations, they've been studied a lot by Marcellini, Lieberman, and many other people, especially in the last years. Okay, so these are related to functionals that have non-polynomial growth conditions, but these are just an example. So, for instance, this is a small perturbation of the standard P growth condition, because you have a log. You can have functionals whose energy is oscillating arbitrarily at any scale between two powers. In this case, it's 3 and 5. And then there's no way that you can control this in like the P-Laplacian case with a P power. Then you can have model cases where you penalize every directional derivative with a different exponent, and therefore you go to the range of anisotropic growth conditions. And you see, once again, you lose this idea that you can bound the same eigenvalues from above and from below by the same quantity. Because here you get a bound from above by the largest power in terms of the gradient, and by the smallest one in terms, again, of the gradient as a lower bound. So all these functionals, they do not fall in the realm of the P growth setting we have seen before. But still they present this, I mean, all this phenomenology goes back really to operators considered in the 70s, in the most general case, by Lipschitz, Seva, Simon, and then there's a literature developing over there. There's a large school in St. Petersburg that, for instance, in the 70s, developed a lot these kinds of non-uniform ellipticity conditions. And then you can go to very, very fast growth conditions, like any arbitrary composition of exponential growth. This functional, as far as I know, was first considered by Duke and Hills in the setting of harmonic mappings. Then it was used by Craig Evans in the setting of KM theory, by Gary Lieberman, by Marcellini. And these functionals have a strange type of double personality, because in principle, it should be easier to prove that the gradient is bounded because you're penalizing a very, very large power of the gradient. Therefore, you force the energy to stay low when you minimize. On the other hand, they are completely unminiatable from other viewpoints because they do not satisfy the delta 2 growth condition. And for instance, observe that the initial integrability condition giving you that the function is finite is destroyed if you put a coefficient which is larger than 1 here. So as soon as you move inside, then you lose all the integrability. Especially this becomes very difficult if you have a coefficient. If you add a coefficient here, then it becomes very, very nasty. This is a recent paper that I have with Cristiana De Filippis, but I'm not going to talk about this. This will be in a future talk. Okay, this is just another example. So the idea, if you go, for instance, if you take as a model case functionals with PQ growth, is that if the ratio between Q and P is too far from 1, then you lose regularity. The ratio measures the difference, this ellipticity ratio, the difference between, I mean, the highest and the lowest eigenvalue. So this ratio measures how fast this ellipticity ratio goes to plus infinity. And it is, so this gives a first indication. So there's a very, very large number of papers devoted to this. And essentially, in the last 2 years, there have been many, many papers devoted to these kinds of problems, starting from those one of Marcellini and myself with Esposito Leonetti. And so this is just a miscellany of bounds. This is a first bound that was obtained many years ago, 30 and 20 years ago in the scalar and in the vectorial case. Then there's a very pioneering paper by Uraltsev and Urdaletova that tells you that if you have bounded minimizers, then you can get Lipschitz continuity with a bound which is n independence, but just for bounded minimizers. And then there's a recent paper by Busquet and Brasco where they have essentially for bounded minimizers and a special structure of an isotropic integrand, there is no bound whatsoever. This is a typical phenomenon when you get a specific structure in the traditional setting of the calculus operations, a specific structure lead to higher information. And then there is this bound, that has been obtained in recent paper by Bella and Schaeffner. These two nice papers on CPEM and on analysis and PDs, when they get these kinds of bounds, of improved bounds. Then there's a recent paper, I just discovered it yesterday, on ArcSIP by Schaeffner. And then there's another paper by Hirsch and Schaeffner, where they have this sharp result for proving that this time the minimizer is bounded, and this is sharp in the setting of the counterexample of Marcellini. And then there's a very nice recent paper by Cristiana De Filippis, Jan Christensen, and Koch, where the bound is got to this newly improved bound. So there's, there's a sort of of game, or who is going to find the best bounds. Okay, now this is as long as the right-hand side is not considered, just for functions with no right-hand sides, so with no data. So what I would like to show is a recent result with Lisa Beck from Augsburg that tells that this linearization program that I showed you before, actually this linearization program can be extended to the non-uniformly elliptic case. So we have seen that in the non-uniformly elliptic case, there's a quantity, there's a crucial quantity. There's a crucial quantity that plays the leading role, which is the ratio between the highest and the lowest eigenvalue. So of course I should add an example like the diagonal matrix here. So for this I say that I bound the lowest eigenvalue and the highest eigenvalue by G1 and G2, which are two general quantities. So these are non-polynomial quantities, are whatever quantities. So this is a very primitive way to express the ellipticity. And then the balance condition Lisa Beck and myself are putting is the following thing. This ratio between the highest and the lowest eigenvalue, which is in the most general case described by this ratio, so will be controlled by a power type function of this natural integrand. So this is the basic condition we find. And so essentially, you cannot do worse than this in the sense that whatever ellipticity means, there will be a lowest and the highest eigenvalue. So you call them G1 and G2. And then the ratio between the highest and the lowest eigenvalue is this ratio. And then you prescribe that this is bounded by a power type of this integrand. Okay. So I'm not going to repart the explicit expression of this quantity because it's not of interest here. I mean, it's the idea just to give an introductory talk when you understand that you are bounding. In a sense, there is a balance between the highest and the lowest eigenvalue ratio and this integrand, which plays a certain role. So just let me give you an example of what is this integrand. So get me, for instance, the P-Laplacian operator. What is G1? G1 is z to the p minus 2. If you multiply by s, then you get s to the p minus 1. Therefore, this is the traditional s to the p. So this is the integrand which is associated to this, this function. So in the classical P-Laplacian case, this is not but s to the p. Otherwise, it is what it is. It is what the functional is measuring the ellipticity. And this is the, let's say, the general balancing condition that we prescribe. Okay, the theorem that we get is that, surprisingly enough, this general principle still persists in the non-uniformly elliptic setting. So for all these kinds of non-uniformly elliptic operators, you get that the same condition that holds in the nonlinear case and actually in the linear Poisson equation case still works for any kind of non-uniformly elliptic operator, provided there's a bit of regularity, or in the case f is equal to 0. So this is essentially the highest, generalization that tells you that there's a general universal linearization principle telling you that whenever you have a divergence type operator, what it matters in terms of regularity of data is completely independent of the growth conditions or of the ellipticity conditions you are using. It's just depending on the structure itself. So it's a universal property. So this qualitative effect comes along with an a priori estimate, which is explicit. And here we get once again this integral with a pole. So this holds, moreover, both in the scalar and in the vectorial case. And this is the a priori estimate, and although it might look weird, this is the natural and the best quantity you can get on the left-hand side. For instance, once again, if you get that, that you're dealing with the P-Laplacian operator, this is just the LP norm of the gradient. This is the LP norm of the gradient in the P-Laplacian case. Moreover, upon assuming that you have a radial structure, which is essentially unavoidable in the vectorial case, otherwise singularities occur, then the same result holds. So the proof is involves some new elements. And the first thing that comes by the proof is the fact that we introduce a new technique. Essentially, we inject some nonlinear potential theoretic techniques that were not used in the setting of non-uniformly elliptic problems. Then we inject this, and therefore we are able to reduce, in a way, the treatment of these equations to the treatment of uniformly elliptic operators. So there's a very fast way to reduce this. And therefore you can, in some sense, the first step is to reduce non-uniformly elliptic to uniformly elliptic problems. And then we go back to the previous stage, and then you reduce nonlinear problems to linear problems. Therefore, you reduce everything to the standard Poisson equation. It's a bit, I mean, it's a bit rough to tell this, but the outcome is the same. So the result essentially covers all the previous general results in the literature, and also it yields new results in the classical uniformly elliptic case. For instance, it gets local analogs and more general analogs of recent results of Chunky and Mazia, published in IAM. And in the case f is equal to 0, it recovers the classical theory of Marcellini, and it recovers also the theory in Orlich setting. So it's a very general fact, and all this, I mean, all these generalities essentially allowed by the fact that we are prescribing ellipticity conditions in the most general form. Okay. So what happens when we particularize these results to the known setting? In the classical case, when f of du is equal to du to the p, so we are in the standard p case, the previous estimate sharply reduces to the optimal one you get in the classical p Laplacian case. This is an estimate obtained by Dutzer and myself first, and then by Tomokous and myself in the most general case. So in the PQ case, so the estimate covers the classical case, covers the classical PQ case, and then in the classical PQ case, you get back to the, when f is equal to 0, you get back to the old result by Marcellini, by Paolo Marcellini, who studied them in this in a systematic way. Then you can go to the unminiatable fast growth conditions functionals, and this is x, for any combination of x. And then you once again that also for these very wild functionals, you get the same result. And this is also in the vectorial case too. So any combination of exponential does, I mean, it can be treated in this way. Okay, when f is equal to 0, the previous result was known, was proved by Lieberman, by Marcellini, but then there was no sharp a priori estimate. Now we are able to get also the sharp a priori estimate in the sense that you can bound du by the log x of du. So dimensionally speaking, you see that this estimate is homogeneous because you have du to the p, and then log cancels an x after taking the expectation, the mean value. And the previous result known was du estimated by x. So you lose a full range of exponential growth. So why we are able to fix this? We are able to fix this because of our linearization principle that allows to reduce the non-uniformly elliptic problem to uniformly elliptic one. And therefore, you get estimates that are typical of the uniformly elliptic case. This is in turn a particular case of a most general corollary, which is this one. You take any functional of this form, where this is just a convex function, so-called n function. It's bad, and with the previous ellipticity conditions, and therefore you get this estimate which has the same flavor. So in particular, you can get x, n times x, then you get n times log. So this estimate was known only under the delta 2 condition that tells you that the functional is not growing too fast. This growth condition tells that the growth of the integrand is at most polynomial. For instance, it keeps everything away when you go to exponential growth conditions. But here we are able to fix this long-standing fact. Actually really 30 years of papers dealing only with these conditions, and then there were no estimates of this type. Okay. There are other results in preparations where we are able to put also coefficients here, and these are very, very, very delicate. These are forthcoming papers with Cristiana De Filippis, but I'm not going to go into that because the situation becomes much more delicate because of this absence of delta 2 conditions. So when you move to point, you lose a lot of things. And also there's a recent paper by Di Marco and Marcellini on the same things, but I'm not going to go to that. So finally, let me talk about another kind of problems. These are, non-autonomous functionals. So non-autonomous functionals, let me briefly give you a flavor of these results. So the idea is that when you get autonomous functionals or uniformly elliptic functionals and you match them with a coefficient, then essentially what you do is to do Schauder theory. Schauder theory amounts to locally make a perturbation arguments around points where the coefficient is continuous, and then you treat it as it were locally constant. This is a general paradigm of regularity, so a continuous or a regular coefficients can be locally treated as a constant coefficient. So let me show you that this is not the case in this setting. So the first surprise comes in this setting. So let me give you these two functionals. So these two functionals were introduced by Zhikof and essentially in the setting of Laventia phenomenon. So in both cases, you see that when you move, so let's concentrate on the second one, which is the toughest one. So when a of x is equal to 0, then you get dv to the p. You have a p growth functional. And when a of x is larger than 0, you freeze it, and then you get a q growth functional. So immediately you realize that there is that the presence of the x is not a perturbation because it's the real source of non-uniform ellipticity. So when you move x, the nature of the functional completely changes. You pass from a p ellipticity to a q ellipticity. So it is actually a weight, and there's a general theorem of weighted problems due to Fabes, Koenig, and Serapioni. This is also connected to that, but I'm not going to go to that. Okay, there's this very old theorem by Fonseca, Mali, and myself that tells you the following. So you get me this very naive functional, which is convex. It's suitably regular. Outside the origin, this is analytic. You can make it analytic also by adding 1 plus something. So this is not the point. So you get a convex scalar integrand with coefficients that are as good as you like. So these are as good as you like. So in particular, you can get alpha between 0 and 1, and then you get C0 alpha. So you are really in the range of Schauder estimates. So according to Schauder theory, minimizers should be regular. But this is not the case because you can get that you can cook up a minimizer with a counter type essential discontinuity singular sets that is as bad as the one of any other competitor. So this is a very, very, horrible construction that gets you that a minimizer can be as bad as any other competitor. So the idea is that P and Q must be close enough according to the rate of regularity. So there's an interaction between the regularity and the non-uniform ellipticity. And this is corrected in this is shown to be the case, because in this recent paper with Baroni and Colombo, we proved that for this kind of functionals, when A of x is C0 alpha, then if you have this bound, then minimizers are regular. Then if U is in L infinity, as in the case of Uraltsev and with Dialetova, you can relax this bound, and the more regularity you get, the more you can relax the bound. So there's an interpolation effect. But the information I really would like to retain is that there's an interaction between there's a quantitative interaction between the degree of regularity with respect to x and the rate of non-uniform ellipticity measured by the growth of this ratio. So there are other papers by Colombo and myself, by Marcellini and co-authors, by Hestro and Ock, by Christiana De Filippis and OH. Then there's a paper by Balci, Dinning, and Surnachov, a very interesting one that proves that also this bound is sharp. And then there are these recent papers, especially by De Filippis. There's a nice parabolic paper by De Filippis. And just let me finish explaining you why this interaction between Q and P and alpha must be taken into account. So if you want to measure the rate of non-uniform ellipticity on a ball where A of x touches 0, then this is given by the sup of the highest eigenvalue on the ball over the inf. So this is a non-local way to measure. It's a non-pointwise way to measure the thing. So you see, you don't fix x, you just take the sup over the inf. And now you see that this grows as this quantity. So there is the gradient component that tends to make this ratio infinite. And then there is something that corrects this. And as regularity is proved by shrinking radius, there's a competition between the growth with respect to the gradient and the ratio. And this is very linked to the counterexample I showed you before, because this is actually a capacitor effect. So take the ball centered at 0, and then you see that this problem comes along with two intrinsic capacities. These are the capacities introduced and studied at length by Vladimir and Marzian, and developed by many people. So there's the standard P capacity, and then the adapted capacity, which takes into account the second piece of the functional. So if you make a computation, this capacity grows as this radius, and this one grows as this radius. So regularity is in some sense connected to capacity, because regularity estimates interact with capacity, determining the removability sets, the removable sets. And therefore, the idea is that if these two capacities, they read different sets, then there will be counterexamples to regularity. So the idea is that these two capacities should not read different sets. So this is the worst capacity a priori, because it is linked to the higher growth with respect to the gradient. So you prescribe the condition under which you can control this capacity with the a priori lowest one. This condition is this. This translates into this, and this is essentially the bound allowing you for regularity. That's the bound contradicted by the example. So the counterexample tells you that if the functional generates two different capacities that are reading two different sets, then there's an ambiguity on removability of singular sets, and then you can generate singularities. If the two capacities, they do agree, and therefore they read the same sets, then there should be regularity, and indeed there is, and then you get this bound. This bound is contradicted by is violated by the counterexample, and this is exactly the one that we get here under this assumption. Let me observe that in the counterexample, the minimizer is bounded. So this is just a flavor of rapidly developing regularity subfield. When you match this non-autonomous information with non-uniform ellipticity. Okay, I think that I can stop here. I told even too much. Thank you.